Hi, I'm Brian Freer, tutoring high school physics. Today's topic, Coulomb's law and electric fields. Coulomb's law tells us the force between any 2-point charges that are focused at a point. And so its force equals Coulomb's constant times the charge measured in coulombs on one of the objects times the charge on the other object divided by the distance between them squared. And that's an R right there. Coulomb's constant is divided by Coulomb squared. If you can't remember these units, just remember that you'll end up with newtons at the end of all this. And you can actually get those units, because as you see, on the bottom here we're going to have meters, and that's going to cancel out with this meter squared. And on top here we'll have 2 coulombs, so Coulomb squared, and those cancel out here, leaving us with newtons. So you'll notice that we've also put both of these in absolute value. Why did we do that? Well, force is a vector, and so that means it takes direction into account. But we can't really if you're working with 2 charged objects, and let me show you why. So these two, let's say they're charged objects, one is positive and the other is negative. Well, opposites attract, and these will be pulled towards each other. But what if they're both positive? Then they'll both be repelled. The same force, however, will happen in either scenario, positive, negative, or positive, positive. But the direction will be different. So that's why we put in the absolute value, to show that we're not actually telling you which direction they're going. With that said, let's actually calculate the force between these 2-point charges. One has a charge of 2 coulombs, the other 2.5. The distance between them is 3 times 10 to the 3rd meters. So we can actually get going. The absolute value of force is the absolute value of K, I'm not going to write all that out quite yet, times the charge on one, 2 coulombs, times the charge on the other, 2.5 coulombs, divided by our 3 times 10 to the 3rd meters squared. Okay, so K, 2 coulombs times 2.5 coulombs gives us 5 coulombs squared. Down here on the bottom, we get 9 times 10 to the 6 meters squared. And so we're going to get some canceling out. We're going to have 9 times 10 to the 6 meters squared is going to cancel out with a lot of this, giving us 1 times 10 to the 3rd newtons per coulomb squared times 5 coulombs squared. And so that leaves us with a force of 5 times 10 to the 3rd newtons. Okay, so that's Coulomb's law. So let's move on to electric field. Anything that's electric is going to emit an electric field, and we're going to represent those by arrows. If we have a positive charge, the arrows will be pointing away from that charge. If we have a negative charge, they'll be pointing towards the charge. If you have both a positive and a negative charge, you'll get this kind of interaction. We can actually find the strength of an electric field at any point at some distance away from the object emitting the field by E equals KQ over R squared, where Q is, of course, the charge on that point charge emitting the field, and R is our distance away from that point charge. So let's get straight into this. Let's say that we're actually going to say this is gone, but we're 3 times 10 to the 3rd meters away from this object of 2 coulombs. So we have our K times 2 coulombs over our distance of 3 times 10 to the 3rd meters squared. So we get a similar equation here. We get 9 times 10 to the 6th meters squared. We're going to get some cancellation between this and K, which leaves us as 1 times 10 to the 3rd newtons per coulomb squared times 2 coulombs. And so that leaves us with 2 times 10 to the 3rd newtons per coulomb. And so that's actually kind of a way of saying if we had a charge that suddenly appeared at 3 times 10 to the 3rd meters away from this one, for every coulomb of charge it would have, it would experience 2 times 10 to the 3rd newtons of force. Alright, to recap. Coulomb's law describes the force between 2 objects, 2-point charges. Force equals Coulomb's constant times the charge on one point charge times the charge on the other point charge divided by the distance between them squared. Note, however, that these are all taken to be the absolute value of those values, because Coulomb's law does not predict the direction in which the force will be facing. If the charges are opposite, then they'll be pulled towards each other, otherwise they'll be repelled. Coulomb's law does not predict this. Electric fields are represented by arrows pointing either away or towards a charged object. If the object is positive, then the arrows will be pointing away. Otherwise, the arrows will be pointing towards it. To calculate the strength of an electric field at some distance r from a point charge, you simply multiply Coulomb's constant times the charge on that point charge and divide by the distance away squared. Alright, that's all for now. Again, I'm Brian Freer. See you next time.